Next factor we are going to discuss is precipitation. You all know about hydrologic cycle, water evaporating from sea surfaces or lakes or such water bodies, and that which is collected somewhere else on the ground, maybe from trees also help in evaporation, or both together called evapotranspiration and so on. And all this water vapor rise to atmosphere to heights because of lower density, and there they get collected and come down on condensation as that is precipitation. It can be in different forms: rain, water droplets of size greater than 0.5 mm. So it can be a drizzle, uniform precipitation. Then it can be snow, hail means sheets of snow falling down, or freezing rain. That means the temperature is that low, the temperature of rain droplets coming down is that low that on reaching ground they freeze whatever surface they reach. So there are different forms of precipitation, so we'll look into that. So I have said, when all the water vapor reaches sky, there it get collected. And for condensation, there are some factors required. There are presence of moisture in the atmosphere. Now, presence of nuclei, it is some catalyst that help in precipitation. It can be dust, or due to fire, if some during volcanic eruptions, some gaseous exhaust may be there, that can help in precipitation. And in ancient India, there was a custom of conducting yagas if there is no rain for a long time. Actually, the science behind this is nothing but presence of nuclei behave as a catalyst for precipitation. Now, favorable conditions for condensation, that is the temperature and so on. No suitable way to reach earth as rain or snow, whatever. Now, this is friend. I have said about favorable conditions. So one among that is friend. Friend means, see, cool air from one side and warm air from the other side. They meet at a point where this rain can happen. Okay, the interface of warm air and cool air. See, northeast trade winds, southwest trade winds meet at some front, there rain can happen. So we have to do this weather forecasting. People go on checking for the wind directions. Cyclone means low pressure region or depression. Now at the center there is a depression around which winds are circulating. At the center there can happen thunderstorms, rain, etc. etc. So we have our monsoon season, during which these depressions are formed in Bay of Bengal and Arabian Sea, and they travel from southwest to North India as two branches, one along western region and the other from Bay of Bengal, both meet at Delhi. So this is the monsoon, that is an example of depression traveling and causing rain. Anticyclone means we have high pressure region at center and wind circulating. Orographic precipitation, that is clouds moving with the wind when these mountains form a hindrance and trees on them can make them come down as rain. That is orographic. Now, with that, we have completed the factors. Now the whole hydrologic cycle takes place due to the heat energy originating from sun. Now just look, we know the law, energy is neither created nor destroyed, so there should be a balance between the total heat energy used. Just look at where all this is used. So there is a heat transferred from water surface to air, and some amount of heat energy is used for evaporation. So some heat is lost into the ground, some heat energy is stored in the water body, and some heat energy is transferred by the water flowing. So we have the heat energy stored in the water body, lost to the ground, transferred by water runoff, and some used for evaporation. This is hydrologic budget equation. That is, earlier we have said about the energy. Now mass. Mass means here what? Water only. The whole amount of water throughout should be the same. Since matter can neither be created nor destroyed, so if we have a particular area taken into consideration and total amount of rain coming down, some is stored within the area, remaining we have surface runoff, subsurface outflow, and actual evapotranspiration. So this is hydrologic budget equation. So I have told both this to get an idea where all energy and matter is distributed. So these have prominent role in estimating the amount we'll be getting, or estimating the amount that will be evaporated, etc. So on. Next, some amount of water is always there which we cannot measure. Just assume this many percentage, and we cannot have any measured quantity, that is interception loss. That is, while the rain is coming down, some amount of water will be stored in the leaves of the trees. We have our terraces in houses and so on. So these actually get evaporated as such. We cannot measure this quantity. Next is depression storage. We have pits all over our ground. water stored there get evaporated as such. In roads and all we have no. Next is infiltration. We have the water quantity distributed as runoff, depression storage, interception loss, surface runoff, ground subsurface outflow, then and so on. Then that flows through evaporation as such during rain or during interception loss and all. So some amount of quantity of water penetrate into the ground, that is infiltration. So in this diagram here we have, if sufficient quantity of water is there, it will go deep into the ground to the wetting zone. So depends upon the quantity of rainfall. First is saturation zone. Water coming as rain penetrating into the ground. The first layer on saturation goes to the second layer, which is the transition zone. There water is transmitted from the saturation zone to the transmission zone, next to the wetting zone. Okay, wetting front. So wetting zone, wetting front, that means there should be some rock strata beneath the ground wherein this water will be collected. So that interface is called wetting front, and where the water is collected is wetting zone. I think you are getting an idea. And I have already said about water penetrating into the ground depends on the intensity of rainfall. So this picture shows how this infiltration depends on the intensity of rainfall. In the first figure, figure A, we have a low intensity rainfall. There water first get into the soil, and if it reaches the saturation level, it will move on to the transmission zone. Okay, then it is transmitted to the groundwater flow, but the soil is not reaching its saturation capacity, so no contribution to groundwater flow. Next, in case of high intensity rainfall, water percolate into the soil gets saturated, then after it reaches saturation capacity, it moves to the transmission zone, then to groundwater flow. Now the factors on which infiltration depends are the soil condition, vegetative cover, current moisture content, type of soil. Soil condition. Soil condition means whether the soil is permeable, loose, which will allow infiltration, but if in case it is dense and impermeable, it will not enhance infiltration. Then vegetative cover actually increases permeability of soil, hence infiltration will take place at a larger rate. Current moisture content means, for example, if I am saying the considered soil, if it is saturated, it will allow no more entry of water, so infiltration will be low. Then type of soil, already said, that is whether it is clayey soil or sandy soil and so on. And the organic content of the soil, etc., everything will affect. Here, infiltration at capacity rate. So what is this capacity rate infiltration capacity rate is the maximum amount of water that the soil will allow to infiltrate into it. So that is the infiltration capacity rate, what they mean by that. So see, dry sandy loam has the maximum infiltration capacity rate, and then we have dry clay loam, then wet sandy loam. So the infiltration capacity rate of wet sandy loam is even lower than dry clay loam, see, initially, because saturation inhibits infiltration. Then comes wet sandy loam, then wet clay loam. Next is Horton's equation. So this is a technique of used to measure infiltration. There are so many other techniques also. So I am just telling this technique because we will be getting an idea of this infiltration. Actually, it takes place at an exponential rate. We have already seen from the graph. With the time, it decreases. See, the infiltration of water with the time it decreases at an exponential rate. So Fp infiltration at any point of time is Fc plus F0 minus Fc into e raised to minus kT, where Fc is the maximum infiltration. Okay, now so at any point of time, that is given by small fp. This capital Fp will consider the amount of water till now what all water has infiltrated. I mean the cumulative quantity. It is of importance because what all quantity of water has infiltrated into the soil. It is the thing which we have to consider. So next, here infiltration capacity of different soils are given. Highly clayey soils, they have very low infiltration capacity, and then sandy loam, then deep sands, that should be well drained. So depends on the type of soil. Now infiltration indices. For calculation easiness, we consider this infiltration to be a constant. I mean not infiltration rate to be a constant for calculation purposes, which is called infiltration indices. Now based on this we usually take into calculation of runoff, etc. So basically this total water precipitated if you are taking the rate. Okay, we have it proportional to runoff. I mean we have the rainfall coming down to be, we take. So factors affecting runoff: type of soil, whether clayey or sandy loamy, such what is the type of soil, and land use or cover. The vegetation available, same as infiltration. See, if infiltration is high, runoff will be low. So if infiltration is high, runoff will be low. In deep clay soil or saturated soil, etc., infiltration is low, therefore runoff expected is high. Now antecedent moisture condition means the water quantity present water quantity present in the soil before rainfall. If it is high, this infiltration is low, therefore runoff is high. So same as how we explained infiltration, the opposite will be the case with runoff. Now, so runoff has adverse effects, like it helps in mass debris flow, and landslide as such will occur in case of clay soil. Okay. Now next, actually the quantities we have to estimate, and whatever quantity is going to precipitate or going to run off, that this landslide or whatever we expect, ground subsurface flow, etc., we need to analyze them. So using today's technologies, we can apply simulation, numerical simulation techniques into this. So here I have attempted to show you the flow chart for simulation of this hydrologic cycle problem. So what all things we can give as input? Precipitation, the amount of quantity precipitated can be measured using instruments like the depth. We will be collecting the water for a region and so on. That is by using rain gauges and all. Now potential, evapotranspiration, temperature, radiation. So these can be measured quantities. These are measurable quantities. We have different instruments for that, and using energy budget equation or hydrology budget equation, we can analyze them. For that, we will be applying simulation. So the function rounded things, that is interception loss, we will be taking a percentage of the precipitated. That's why it is given as a function. Now impervious area, for that we will be taking the type of soil, and that is a function of that soil on impervious area. Infiltration, it is also a function. We can give equations like Horton's equation, etc. Next, surface runoff, inner flow takes place, upper zone storage. Then upper zone depletion, it is again a function. Then storage quantity means it is a particular quantity stored as such. Okay, we have that as a constant value. Now similarly, the other things, say we have overland flow, interflow. These are all functions of the runoff. A particular percentage of the runoff we can give, so and so. You can see what all stages this evapotranspiration take place to, from interception losses, then from storage, depression storages, from lower zone storage, that is even after groundwater storage. You can guess from what they are. That is this from groundwater storage only, these plants are absorbing water which is getting evaporated, that contribute to precipitation. So similarly, so this is the way you can simulate the problem of hydrologic cycle. Using numerical simulation techniques, you can solve that. So another important thing is soil piping, that is after effect of precipitation only. During heavy precipitation times, there can be a change in the hydraulic gradient. This soil piping has observed in many parts of Kerala even. Simply it is seepage of water through soil due to hydraulic gradient difference. That is, in dams, in dam soil, under the structure, concrete structure, there can be a water flow. See, if the exit gradient, so if I am showing you that this is the dam, water can flow like this to up. So if this is the portion where water is stored, this seepage of water like this can cause damage to the structure. So that is soil piping. So there is Goslar's step-by-step procedures to identify whether this soil piping take place and all, for protection of hydraulic structures like this. We can construct a concrete structure like this, so that this hydraulic gradient is given by delta H by L, and if this length increases, see this phenomenon, there can be the risk of this reduction in the risk of this kind of thing. So that is why increase the length of concrete structure base like this. Okay. Now from flow net and all things also you can identify this hydraulic gradient like this. Equipotential lines are also drawn, so you can find delta H by L and find out whether the hydraulic gradient can cause a damage to the structure. Next, an associated phenomenon is liquefaction. So liquefaction is actually it is soil, boiling of soil. In many cases you may say it happens in sand only. When the shear strength or effective strength of soil becomes zero, that is, whatever soil is held there, whatever soil we are considering at any depth is held there because of some vertical stress downwards. Suppose this stress is zero, means what? It comes up, or boiling, kind of boiling only. So I can explain this liquefaction with the help of a diagram. That is the stage when the effective stress becomes zero. So if I am considering a soil stratum like this, then water collected above that, to measure hydraulic gradient or water pressure at this point, I have used this arrangement, and the water, so this pore water pressure is basically because of capillary rise. So suppose this much height water rises to this arrangement, so that can be considered to be the water pressure at that layer. Okay, now the soil particles experiences stresses due to adjacent particles as well as due to the pore water particles. Okay, So the effective stress, if I am considering, effective stress, so suppose H1, H2, we have gamma W H1 plus that of soil particles which is submerged within water. So to get that of soil particles alone, we do gamma sat minus gamma W into H2. So at this layer, the effective stress is this much. Minus, again what? We have the hydraulic gradient. Which is nothing but gamma W H from this diagram. Okay. Now this hydraulic gradient is H by L, or the total length, which is H1 plus H2. So gamma sat H2 plus gamma W into H1 minus H2 minus H. So this is the effective stress we are getting. So we know H minus so on further solving you will get that where gamma sat H2 minus or plus gamma W into H1 minus H2 minus H. This gamma saturated is nothing but G gamma W from the equations of soil mechanics. It is nothing but one plus C. Again solving this gamma W, this can be equated to 0. For the liquefaction condition, we have sigma effective as 0. So therefore from this on solving, what we will be getting is G minus 1 by 1 plus E is equal to H by total length H1 plus H2, which is nothing but hydraulic gradient. So this is the condition we have to check for to prevent liquefaction. Okay, so with this I am concluding the effects of precipitation. Means we have considered several factors. At all levels there can have failure of slopes leading to slopes or failure leading to landslides.